Today, we're going to go around the unit circle and take all the angles that we know around the unit circle, all those common angles, the important ones, the 30, 45, and 60 degree reference angles, and the quadrant angles, and we're just going to translate them into radians. And then we're going to look for patterns so we can learn our radians and make associations with the degrees. The reason that radians is a little more burdensome is that we're going to make fraction multiples of pi, and generally people just don't like fractions very much. I don't know why, everybody's got to be all number racists, but you know, fractions are numbers too. But let's practice counting in fractions. Remember, the big idea behind radians is that a full circle is going to be 2 pi radians. This is because back in the day, we decided that pi should be the ratio of the diameter, the circumference to the diameter, and not the circumference to the radius. Like I was there. So this was a big mistake on our parts, but it's what we have to live with. It'd be much better if we had gone with the circumference to the radius, because that's kind of more defining what the circle is. And it's certainly be more convenient now that we have all this trig stuff to deal with, but we got to go with what we got. So let's see how it works. This way, we're going to get better at fractions anyway, so it's a win. All right. First thing we want to point out is that, remind ourselves, is that 360 degrees is one full circle, and 2 pi radians is one full circle. So we're just going to be taking this 360, replacing 180 degrees with pi, and making a bunch of fractions going around this circle. I've marked off our angles that we got to know, our 30 degree reference angles, our 45 degree reference angles, and our 60 degree reference angles going around the circle. I got the 30 degree reference angles in red, the 45 degree reference angles in green, and the 60 degree reference angles in blue. Let's remind ourselves of what these angles are. In the first quadrant, 30 degrees is just 30 degrees. A 30 degree reference angle in the first quadrant is just 30 degrees. A 30 degree reference angle in the second quadrant is 180 degrees minus this 30 degrees, or 150 degrees. In the third quadrant, a 30 degree reference angle is 180 plus 30, or 210 degrees. And in the fourth quadrant, a 30 degree reference angle is 360 minus 30, or 330 degrees. These are all of our 30 degree reference angles. Let's learn these reference angles in radians. The key thing that I want to start with is that pi radians is 180 degrees. That's what I want to use as my basis, because I'm going to write fraction multiples of pi all the way around this circle. So I should know that pi is equal to 180. So I'm going to make a note down here, and I'm going to realize that I made my circle too big, so I can't keep notes and then like circle at the same place. I think it's because I'm going to need this space. But anyway, we're going to note that pi radians is 180 degrees. So this is going to give us the fraction multiple of pi, that's 30 degrees. To go from 180 down to 30, we just need to divide by 6. So turning 180 degrees into 30 degrees, we just divided by 6. So 30 degrees is pi over 6 radians. So all we have to do is divide by 6. 30 degrees is pi over 6 radians. So note that I had to put units on the 30 degrees because I was about to write 30 equals pi over 6. And y'all are going to be thinking that's not true. But 30 degrees is equal to pi over 6 radians. And that raises the question, why don't you write radians? And the answer is, we just don't. we just understand that the pi over 6 represents radians in this context, so we don't need to write radians. Now I'm just going to follow this all the way around. So I like to start off with this 30 because the 150 is just 5 times 30. So if I want since 150 is 5 times 30, 150 degrees in radians will just be 5 times pi over 6 radians. So 150 degrees is 5 pi over 6 radians. Two styles that we can write are fraction multiples of pi. Sometimes we write pi in the numerator, sometimes we write pi on the side. You have to decide which is going to be your style. I'm a pi in the numerator kind of guy, but you might be, that's crazy, Leach. What do you want to do that for? You should write this as 5 pi or 5/6 times pi. So pick one of your fraction multiple of pi writing styles, and then we can go and fight about it on the internet in the comments section. Plot twist, I turn the comment section off on all my videos. So pi in the numerator is going to be the way. Seriously, it doesn't matter. So the way I got from I took the 150, I said that's just 5 times 30. So if I do 5 times 30, that's going to be 5 times pi over 6. Going around the circle, the 210 is 7 times 30. And so 210 degrees in radians is 7 pi over 6. (210 degrees is 7 pi over 6. Once again, we're just using the fact that 30 degrees is pi over 6 and multiplying it by 5 for 150 and multiplying it by 7 for 210. So 7 times 30 is the 210. And so we get 7 pi over 6. And then the last one, 330. 330 is 11 times 30. So this is 330 is going to be 11 pi over 6. So notice that all of our 30-degree reference angles are pi over 6 degree or pi over 6 radian reference angles. And they all keep that denominator of 6. That's helpful. Let's go on and do the same thing for 45-degree reference angles. So pi is still 180 degrees, and we get the 45 if we take the pi and cut it in half, we're at 90. And if we cut 90 in half, we'll be at 45 degrees. So a 45-degree angle, we'll just take pi, cut it in half for pi over 2 for 90 degrees, cut pi over 2 in half, and we'll get pi over 4. If you double the denominator, you cut the fraction in half. Now we're just going to count in 45 degrees around the circle. 45 degrees is pi over 4. 245 degrees is 90, so that's 2 pi over 4. 345 degrees is 135. That's going to be our other 45-degree reference angle, or one of our other 45-degree reference angles. And 135 is 3 pi over 4. We can just count around the unit circle in units in steps of 45 degrees. So I could look at the pi over 2 as 2 pi over 4, because 90 is just 2 times pi over 4. But we would simplify that to pi over 2. So I could go around the unit circle, 45, 90, 135, 180, and think of it as pi over 4, 2 pi over 4, 3 pi over 4, and then 4 pi over 4. Now we're just counting in units of pi over 4 and simplifying when we can. So I got 4 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. So the next one at 225 will be 5 pi over 4. The next one after 5 pi over 4 is 6 pi over 4, where we're at 270. But 6 pi over 4 we can simplify to 3 pi over 2. The next 45-degree reference angle is 315. And since 270 is 6 pi over 4, 315 is going to be 7 pi over 4. And then we'll finish off at 360, which is 8 pi over 4, which we simplify to 2 pi. We're just counting around the circle in pi over 4. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. See, counting in fractions, not so bad. It just changes what the step size is. And all we're doing is we're starting off with pi is equal to 180 degrees. And if we divide by 4, (45 degrees is going to be pi divided by 4. Same thing we did to get 30 degrees from 180, we divide by 6. Now we're going to do the same thing with our 60-degree reference angle. Once again, we're looking for patterns. We don't just want to sit down and start memorizing these pairs of numbers. We want to start learning the patterns so that it's easier to associate these numbers. I'm going to start off with the pi radians is 180 degrees again. And I want to figure out how to turn 180 degrees into 60 degrees. And that means we need to divide by 3. And look how much better things are in fractions, because to divide 180 by 3, I had to know that 18 divided by 3 is 6. But if I want pi divided by 3, I just write pi divided by 3. Fractions are awesome that way. Fractions like, oh, you don't need to know your times tables. Just put the 3 in the denominator. That's how you divide by 3. Now you can probably guess what we're going to do. We're going to do the same thing. I'm going to count around the circle in 60-degree jumps, because 60 degrees now pi over 3. So 60 degrees is 1 pi over 3. 2 times 60 is 120. That's our 60-degree reference angle in the second quadrant. And 120 is 2 times 60, so it must be 2 pi over 3 radians. 120 is 2 pi over 3 radians. 3 times 60 is 180, and that would be at 3 pi over 3. So this 4 pi over 4 is also a 3 pi over 3. But we would simplify that to just pi. 4 60s is 240. That's our 60-degree reference angle in the third quadrant. And it's 4 60s, so it's 4 pi over 3. 5 60s is 300. And so 5 pi over 3 is 5 pi over 3. Then we get around to 6 pi over 3, also known as 2 pi. And that's where we're back at 6/60, which is 360. So here we are at 6 pi over 3. So we've counted around in pi over 4, which is 45 degrees. And then we counted around in pi over 3, which is 60 degrees. It landed us at 60, 120, 180, 240, 300, and 360. The 60, 120, 240, and 300 are our 60-degree reference angles in the first, second, and third and fourth quadrants. So our reference at 60-degree reference angles are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Now, notice that we didn't count around in pi over 6s. We just started off with 30 degrees as pi over 6, and then we went directly to the 150 degrees. Notice that if we count in 30s, we're going to land on all the 60s, because 60 is just 2 times 30. So the 60, if I start counting, if 130 is 1 pi over 6, then 2 30s is 2 pi over 6. 2 30s is 60. So pi over 3 is also 2 pi over 6. That's why we didn't count in the pi over 6s, because they get simplified to pi over 3. 3 30s is 90 degrees. So that would put us at 3 pi over 6 up at 90. 120 we can also read as 4 pi over 6. 150 is the 5 pi over 6. We already got that one. 180 would be 6 pi over 6, and we can just keep counting around. 210 is 7 pi over 6. 8 pi over 6 would actually simplify to 4 pi over 3, and that's the 240. 8 times 30 is 240. 9 pi over 6 is 6 pi over 4. I didn't leave enough space. 10 pi over 6 is our 5 pi over 3. 11 pi over 6 we already have at the 330. And 360 would just be 12 pi divided by 6. So now we have to know the unit circle in 2 different ways. From 0 to 360 in degrees, and also from 0 to 2 pi in radians. We got to count in 30s, 45s, and 60s, which means we got to count in pi over 6, pi over 4, and pi over 3. It's all very organized. It's just it's more natural to multiply by 30 than it is to multiply by pi over 6. It just looks weird. Any questions? Once we get this association between radians and degrees, and it becomes automatic. So I say 7 pi over 6, and you immediately think 210 degrees. And then I say 300 degrees, and you immediately think 5 pi over 3. You want to think all the other things that go along with it. When I bring up 300 degrees, you want to immediately think of 5 pi over 3 and 60-degree reference angle. Or if I say 135 degrees, you want to immediately think 3 pi over 4 radians and 45-degree reference angle, or pi over 4 reference angle. If I tell you 7 pi over 6, you want to think 210 degrees and a 30-degree reference angle, or a pi over 6 reference angle. So we have two ways, which means we have to know both. Any questions? This is one of those things that makes much more sense instead of using pi to use, instead of pi being half a circle, it would have made more sense to have pi be a full circle. But we've been doing this way for so long, even though it makes so much more sense and the fractions will work out easier, it would be a bad idea to switch. Like, it would be really convenient if we would all agree to put the driver's side of the car on the left side, just for example, and then all drive on the same side of the road. But we don't, and if we tried to switch now, it would be a complete and utter disaster. So we're just going to have to live with the different ways of doing things. Although it'd be really handy if in the United States we would learn to measure things like the rest of the world does. I mean, just, I could probably give up on that as long as the British would stop making fun of Americans for not using the metric system, because you don't get to use both and then make fun of people for using the system that you invented. You don't get to say, haha, they don't use the metric system, and then go to the pub and order a pint. You know, get over yourselves, entire country. No one watches my videos, so I'm safe. All right. So your job is to learn your angles going around, your angles in degrees and radians, the ones that we've marked as important. Anything on the quadrant, so multiples of 90, anything with a 45 reference angle, anything with a 30 reference angle, anything with a 60 reference angle. The ones that you should focus on are the simplified ones. So we don't want to say 8 pi over 4. We want to say 2 pi. That's the one that we want to focus on. We want to say pi over 3, not 2 pi over 6. We want pi over 2, not 2 pi over 4 or 3 pi over 6. So focus on the simplified ones. I just realized I don't know if the highlighter is showing up, but it looks like it is. So focus on the simplified ones, but know that the other ones are available, because you want to know how all these things are connected. That will help you remember all of your angles in degrees and radians. Look for all those patterns. Count around pi over 6, count around pi over 4, count around pi over 3. And that'll help you make those associations. Any questions? All right. The reason that we want to do this is that we want to take our unit circle and start stretching it out, so that instead of theta going around in a circle, we want theta to go left and right. We want theta to be a horizontal axis. So we want to look at graphs of sine and cosine. So you want to look stuff up on Wikipedia, you're looking for sinusoidal functions. And now every time, this is one of those words that every time I write it down, I'm like, oh, did I spell that right? Sinusoidal. Sinusoidal. Okay, good. It's one of those words that never looks right to me, but there it is. Graphs of sine and cosine. These are sinusoidal functions are a type of function called periodic functions. So they are also, these are periodic functions. Let's say a kind of So what we mean by periodic functions is that they'll do, they keep doing the same thing over and over again. So they do a bunch of different stuff for what we'll call one period or one cycle. And then the next, over the next period, they do the same thing. So if we look at the graph of sine, I need to switch to radians. When we look at the graph of sine, we see that from 0 to 2 pi, because I have it in radians, it goes up, down, and then up again. And then from negative 2 pi to 0, it did the same thing. It's just a copy. And if I increase the window to include more of the x-axis, there's 1 cycle, 2 cycles, 3 cycles. So it's just going to keep doing this same thing. Go to the left, go to the right. There's 1 cycle, 2 cycles, 3 cycles, 4 cycles. It's just a copy of what it does between 0 and 2 pi. So let's talk about our base sine and cosine functions, and then we'll talk about how to modify our sine and cosine functions. So just like before, we want to know this information in degrees and radians. So it's easiest to set this up with degrees, but we're also going to want to set it up in radians. So 90 is pi over 2, 180 is pi, 270 is 3 pi over 2, and 360 is 2 pi. So we should know our angles in degrees and radians. So I'm going to put theta down here on this horizontal axis. So instead of going around the circle with theta, I'm going to have theta go along this horizontal axis. And on the vertical axis, I'm going to put the sine of theta. So I'm going to make the graph of sine of theta. Now, I didn't give myself a lot of space on the vertical axis. I go up to 1 and down to -1. That's because as theta goes around the circle, the sine of theta is the y coordinate going around the circle. And if we're on the unit circle, we're at most going to be 1 unit away. The largest value of sine of theta that we see is going to be 1. The biggest y coordinate that we see is 1. The smallest y coordinate we see is -1. So we're going to be always in between 1 and -1. That's the top and the bottom. So looking at our unit circle, we're now thinking of the coordinates. At 0 degrees or 0 radians, the y coordinate is 0. And then at 90 degrees, the y coordinate is 1. At 180, we're back down to 0. At 270, we're at -1. And then at 0, we're back to 0. So we get theta is 0, sine of 0 is 0, sine of 90 is 1, sine of 180 is 0, sine of 270 is -1, and sine of 360 is 0 again. And I knew that 3 pi over 2 wasn't going to fit there. I thought about it so long where to put the 3 pi over 2, and I'm like, oh, it needs to be above, along with the 270 needs to be above as well. I'm like, oh, nah, I'll still write it below. If you had like a professional teacher, they probably wouldn't make mistakes like this, but you got me, so. What happens when you get your math teachers just off of Craigslist. I'm kidding, it wasn't Craigslist. It's Facebook Marketplace, which is infinitely worse. Now, we don't just want to connect these with lines, but we see this. This is generally what we saw with our graphing calculator. It started off at the middle, went up, down, down, and then up. So it's got this flow to it. Now, it's a little bit more curved than that. It's not just straight line up, straight line down. Remember, the halfway happens at 30-degree reference angles, or pi over 6 radian reference angles. So we hit halfway. We hit halfway at our 30-degree angles. And I marked it off in 3s here. I marked it off in 3s here because half is easier to find than 0.7071. So if at 30 degrees, or pi over 6 radians, that's when we're halfway. And that happens before the halfway horizontally between 0 and 90. So that shows that it's kind of bent up. Instead of a straight line from 0 to 1, it's kind of bent this way. That's going to curve the graph. And it goes flat at 90 because it's turning around. So that's one way we can get that curve going, because we know that the sine of 30 is equal to a half. We know we're going to hit a half again when we get to 150 degrees, which will be 30 degrees before 180. So that's going to be 5 pi over 6, because we're doing it both ways now. And so at 5 pi over 6 will be at 1/2. There's a lot going on here that we can associate with the stuff that we've done before. Notice that from 0 to 90, here we are in the first quadrant. So if we start breaking this down into quadrants, here we are in the first quadrant. And we know that sine of theta is positive in the first quadrant, and there's the graph above the theta axis giving us positive values in the first quadrant and the second quadrant. And then we're going to drop down negative in the third quadrant and the fourth quadrant. So at 30 degrees after 180, we'll be at a negative 1/2, because we have a 30-degree reference angle. Here's the nearest x-axis, 30-degree reference angle, or pi over 6 radian reference angle. And so that the sine of 30 is 1/2, and we're in the third quadrant, so it's going to be negative. It's going to be flat here at 270. But I just need to connect this through the 1/2. That happens a little earlier because I'm not making a line, and then flat it out. And then the next 30-degree reference angle is 30 degrees right before the 360. So that's the next place we're going to be at 1/2. And there's our graph of sine. This is one cycle of sine. It takes us 2 pi radians to get through one cycle. So we say that the period is equal to 2 pi. The period is the length of one cycle. And so the period is 2 pi. And these points come from the y-coordinate going around the unit circle. I didn't try to mark all of them, but I like to go for the 1/2 and negative 1/2. Because that's enough to get that bend. And the 1/2 is much easier to find on the grid to see how much how it's bent up. Check the concavity. We think of a line between the 0, 0, 0 and pi over 2, 1. A line, we'd be halfway at halfway. But because halfway happens before, that bends this so it's concave down. It gives this concavity facing down. And the same thing, instead of going, a line would have halfway be at halfway. But since the halfway happens after, that gives us this concave down, this concavity. Once again, there's a lot of relationships that we want to make between this and our unit circle. And we want to know the values in degrees and in radians. We don't have to worry about degrees and in radians on the sine because sine of theta is not measured in degrees or radians. It's not an angle. Let's do the same thing for cosine. So let's do the same thing for cosine. So each mark on my grid is going to be 30 degrees like it was before, or pi over 6 radians like it was before. And once again, since we're going with the x, so x is cosine theta. and theta is on the horizontal axis. Since we're going around the unit circle, the largest values of cosine are going to be 1 and -1. So I don't need any more graph other than anything above +1 or below -1. Cosine will always be between -1 and 1 because the x on a unit circle is always between -1 and 1. But now going around the unit circle, we're going to be starting off at 1 because we're looking at the x coordinates. So the x coordinate at this point is a 1. And then when we get to 90, it drops down to 0. The x coordinate is 0. At 180, the x coordinate is -1. And then at 270, the x coordinate is 0. And then back to 1. So instead of starting off at the middle, going up, down, down, and then up, we're going to start off at the top. Cosine of 0 is 1. Cosine of 90 or cosine of pi over 2 is 0. Cosine of 180 is -1. Cosine of 270 is 0. And cosine of 360 is back to 1. We have to know this in 2 different ways. So cosine of 0 is 0. Cosine of pi over 2, cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is back to 1. We don't have to stop. We don't have to memorize all these values. We just have to remember them. So we got a graph that starts at the top, goes to the, down to the middle, down to the bottom, back up to the middle, back to the top. I'm going to use the 1/2 again, but in this case, since I'm dealing with cosine, the reference angle that I care about is 60 degrees. So I'm going to grab the blue pen and say 60 degrees is where we're going to be at 1/2. And then I'm going to draw it flat up at the top. And then I'm going to have this graph kind of concave down. It's going to be pushed, it's going to be bent concave down because we're a little past halfway on the x when we hit halfway on the y. Just like before, here we are in the first quadrant. And we can see that all the values of cosine are positive in the first quadrant. We're at a 60-degree reference angle, which is a pi over 3 radian reference angle. The next reference angle where we hit a -1/2 in the second quadrant. The 60-degree reference angle in the second quadrant is 120, or 2 pi over 3 radians. And that's the next 1/2. A 60-degree, the cosine of 60 is 1/2 in the second quadrant. 120 degrees has a 60-degree reference angle, and cosine is negative in the second quadrant. So that tells me how this the graph should be bent. I'm not just going to draw a line between these 2 points. I'm going to bend it a little bit so it's concave up so I can hit this halfway point before I'm halfway horizontally. And make sure it flattens out when I get to 180 because I'm turning around and heading back up the other way. Next, we need a 60-degree reference angle in the third quadrant. And the 60-degree reference angle in the third quadrant happens at 240, 60 degrees after 180. also known as 4 pi over 3. And finally, back in the fourth quadrant, cosine is positive because x coordinates are positive in the fourth quadrant. A 60-degree reference angle in the fourth quadrant happens at 300 degrees. And the cosine of 60 is 1/2. So there we are halfway. It's a little bit before horizontally halfway between 270 and 360. So here is the graph of one cycle of cosine. And the period of cosine is also 2 pi. Because once we've gone around the circle one time, the x coordinates are just going to do the same thing going around the circle. So the period is once again 2 pi. This took a lot of time for us to draw out, because if I want to just look at the graph of cosine, if the point of the exercise is just to do it fast, then I can just have my calculator produce a graph of cosine. But the point is not to just produce the graph of cosine. The point is to use the graph of cosine and draw, by the process of drawing the graph of cosine, to learn our values in degrees and radians, and to learn our reference angles. We can also use this 1/2 business to get the that we're using to get the concavity to right, to reinforce our values of sine and cosine, and associating the sine of 30 with 1/2 and the cosine of 60 with 1/2. We're connecting these, even though they're just facts that I want you to remember, we're making more connections in different contexts, so it's going to be easier to make those connections. And we're going to remember things more because we have more ways of remembering them. More ways of remembering things, always better. More connections between seemingly different concepts, always better. If we taught algebra as an arithmetic class, I think it would be a lot easier. Any questions? How's everybody okay? I can't tell. I'm just kind of mostly looking at like pictures of names and stuff like that. There should be a way on, I mean, you can also use like thumbs up and stuff like that, which is really cool. But like, it'd be cool if you put like a question mark, like your name went italicized or something like that. So there'd be like a more of a visual cue that's like, hey, what's going on? Because one of the things that I noticed in the reactions, all the reactions seem to be positive reactions, like clapping, a thumbs up, a heart, a laughing, a surprise, and then another kind of surprise. There's nothing like, there's no like, they need, oh, it looks like they've included some more. They need like the crying ones. Yeah, that happens a lot in math classes. That should be one of the default emojis that you should be able to like cry a bunch. Because I mean, that happens a lot. So I guess they've included some more, but it used to be that you only got like the happy ones. And if you use the exclamation points, the sound effect that plays in my head is that Metal Gear Solid exclamation point sound. Do you know what I mean? Some of you know exactly what, some of you heard it when the exclamation point happens. Okay. Because the guard has just sensed your presence or something. You know what I mean? How's everybody okay?
Yes.
Cool. So I'm not asking you to memorize your values going around the unit circle in degrees and radians. I am asking you to remember the values of sine and cosine in degrees and radians going around the unit circle. Learn your reference angles, learn your 1/2, √2/2, √3/2. This will help, these graphs will help you remember those values. Because if you remember sine goes up, down, and then up again, that'll help you remember that since 30 is the first thing that happens after 0, that third sine of 30 is a 1/2. But cosine of 30, since cosine starts at the top, cosine of 30 is √3/2 or 0.8660. The reason that we want to recognize what how these graphs work, and we want to really have a good handle on these graphs, is because we want to be able to adjust the graphs. So here's our default graph of sine. But what if the thing that we have, the thing that we're measuring, doesn't go between -1 and 1? What if the amplitude, the distance from the middle to the top, what if the amplitude is bigger? Like it's twice as much. So if let's say, what if we had 2 sine of x? So notice that when I multiply by 2, I don't change the period or where the graph hits the x-axis, but now I'm going between 2 and -2. And if I go up to 3 sine of x, once again, I'm not changing the period. I'm adjusting how much amplitude we have. The distance from the middle to the top is whatever that coefficient is. Any questions? This raises another question. What if I make that number negative? What if I put -3 times the sine? Before I hit enter, think about what that might do. How would changing the 3 sine x to a -3 sine x, what's going to happen to the graph? So here comes -3 sine x. What does it look like happened?
Is it shifted down 3 units?
It didn't shift down 3 units because we're still between 3 and -3. Shifting down 3 units would be between 0 and -6. That would be, and it would maintain that shape. What happened? Get rid of this extra noise. Turn these two off. Let's just compare 3 sine x and -3 sine x.
It's upside down.
Looks like the multiplying by -1 made it upside down. This is an association that we want to make. If I multiply after the trig function, that's going to stretch things, because all I did was stretch it when we multiplied by 2 and 3. That stretched it vertically. Nothing happened side to side. And then if I multiply by -1, it ends up being upside down. It gets flipped over the x-axis. So if you will run up to someone, grab them by the waist, and then turn them upside down, you multiplied them by -1. But watch what happens when I do a different multiplication by 2. Let's turn the sign back on again. What if I multiply by 2 for 4? So now what's happening, the sine of 2x is the red one. And look at the sine of 2x is going through cycles twice as fast as the sine of x. The sine of 2x has a circle between 0 and 360. It's going to go around that circle twice as fast as sine of x. Because when x is at 180, 2x has hit 360. So that's why the sine of 2x is going so much faster. That 2 is making the x's go twice as fast. So notice that what happened is that I've multiplied. I didn't change the amplitude at all. I multiplied before sine took place, and I squished the graph in. I compressed it. Any questions? So let's look at another thing. What happens if I take sine x and just add 1 to it? Actually, I have enough space. I'm going to add 2 to it since I've been using 2. So notice that now my operation, I'm still using a 2, but I'm not multiplying by 2. I added 2. Maybe it'd look better if I do sine x, close parentheses, and then added 2. Just take what I think I had before and add 2 to it. What's this going to do to the graph? Think about what effect this will have on the graph before I hit enter.
Shift right.
Shift to the right. I like the shift part. Let's see. What does it look like happens here? Looks like I'm getting a copy of the graph, but it shifted up. The addition told us there was going to be a shift. The addition made a shift, whereas multiplication made a stretch. The reason that this was a shift up was that +2 happened after the trig function. It happened after the sine of x. Because if I take the sine of, if I turn this one off, if I make the +2 happen before the trig function, if I put it in the parentheses, now the +2 happens before the trig function. So the addition means it's going to be a shift. But since it happened before, it shifted the graph horizontally. So it's hard to see where the middle is, but here's sine of 0 is 0, and the other one is sine of -2 is equal to 0. So putting a +2 shifted the graph to the right 2 units. Shift because positive, horizontal because it happened before the trig function. Because what we want to do is observe something that's going to be a periodic periodic function or a sinusoidal function that's not necessarily going to have the top at 1 and the bottom at -1 and the middle at 0. Maybe the bottom is at 5, the top is at 20. And instead of the period being just 2 pi all the time, what if the period was 20 minutes? We see something happens and it's just going down and then back up again, and that takes 20 minutes. How are we going to write a function that represents that? So we're going to have to learn how to adjust the period, how to adjust the amplitude, and then how to shift vertically, and also how to shift horizontally. What we're going to find out is that shifting is addition, stretching and squishing is multiplication. Before the trig function will be horizontal stuff, either a horizontal shift or a horizontal squish. After the trig function will be vertical stuff, either a vertical stretch or a vertical shift. And -1 will flip things over. When we did negative sine, we flipped it over the horizontal axis. If I multiply by -1 beforehand, we'll flip things over, but -1 before the trig function is a horizontal stuff. That'll happen around the vertical axis. Heck, I guess I just slid right into chapter 4. I thought it was going to be an afterthought. I'm like, oh, let's just do chapter 4. Addition is shifting, multiplication is stretching, multiplying by a -1 is flipping. Before the trig function is horizontal stuff, after the trig function is vertical stuff. Also, the horizontal stuff seems backwards because we did a +2 and they shifted to the left. All right, that was a lot. This seems like a lot to remember, but that's only because it's a lot to remember, and you have to remember all of it all the time in perfect detail. So I'm not asking that much. Take next couple of days. Make sure you learn your common angles in degrees and radians, along with their reference angles, along with their sines and cosines. We're going to continue looking at graphs, and we're also going to be looking at some trig identities. So we're going to look at some relationships that between the trig functions, because they're all related. We get them all out of the same triangle. We should expect them to be related in some fashion. But for now, we need to know our values. So take some time, learn your values. That's going to do it for today. I'll see you all on Thursday. Everybody have a good couple of days, and thanks for playing.